Suppose we're given the PDF f for a continuous random variable. We'll assume that f is piecewise continuous. This means we can find the CDF by integration, which will also be a piecewise continuous function. On each interval, the derivative of our CDF is going to be our PDF. So we can recover the PDF except at the boundary points. For example, suppose a random variable has cumulative distribution function. Let's find the PDF for non-boundary values. We can differentiate as long as we lose the values at the boundary points. So we find the derivative of each of the piecewise components. And so this will give us our PDF at all of the non-boundary values. What happens at the boundary points? In general, if x is a continuous random variable, the probability that x is any specific value is 0 for any a. However, in some cases, that probability might be non-zero. This is sometimes called an atom. Informally, if our probability isn't 0, then our probability density function has to have value infinity. The problem is that infinity is not a number, so formally, this requires a much more advanced course. So we won't sweat the details here. But if we return to our CDF, we could talk about the probability that x is 1 and x is 4. So remember, a problem exists whether or not you know how to solve it. Note that x equals 4 is in one of the intervals where our CDF is continuous. So this means it's also in an interval where f is continuous. And so that means the probability that x is 4 is going to be 0. However, x equals 1 is at the boundary between two intervals. So consider x very close to but less than 1. Note that the limit as x approaches 1 from below of our CDF is 0.5, but our CDF at 1 is 0.75. So when x equals 1, there's a jump to discontinuity. We can interpret this as follows. Including x equals 1 in our interval causes the probability to increase by that jump, and so the probability that x equals 1 is 0.25. So remember, concrete doesn't hurt. Consider the probability that x is less than or equal to 0.69 and the probability that x is less than or equal to 1. Now, the probability that x is less than or equal to 6 nines is our CDF at 6 nines. And since that's strictly less than 1, we'll use our first formula and find, which is pretty close to 0.5. But our probability that x is less than or equal to 1 is our CDF at 1. However, the rule changes at x equals 1, giving us 0.75. And what this means is that including x equals 1 in our event changed the probability by 0.25. And so it follows the probability that x equals 1 must be 0.25.